Now it will slowly come also the title. Yes, now it's entirely there. Thank you. Go ahead.
Thank you very much for the possibility to talk about 6 quarks, so-called Dibaryons. And we concentrate, of course, on the unflavored sector, where we think we found some evidence for it. And hopefully in the last minutes to have also some perspectives in the flavored sector. Now, in this workshop, we talked a lot about tetraquarks. Is it a compact object or meso-meso molecule? Pentaquarks, the same situation, compact or more molecule. The same situation can be extended to the hexaquark system, whether it's a compact object or more a baryon-baryon molecule. So we go now from baryon number 0 to baryon number 2. Now the question is, what do we really know? And here I'm really jealous about the wonderful spectra we saw in the meso-meson and meso-baryon scenarios in the recent days from LHCb or from GluX or whatever. Now, if we look now what is the situation in the 2 baryon scenarios, we have to confess we know very little from it. What we do know really is only just one bound state, the neutron ground state. And we know the one S0 vertical state, which you know from nuclear-nucleon final state reaction. And in addition, if we go now to a strange system, lambda n, we also know the final state interaction. So what we would like to know, of course, is there more? Are there indeed genuine dibaryons, hexaquarks, or are there a general resonance state, like at least molecular state or dynamically created state at all? Now, I will concentrate what we know so far from experimental finding, and that's the so-called 1D2 resonance structure at the delta n threshold, which would be an isovector 2+ state, which we know, or where we have hints for it already since the 50s. And then we have the 3D3 resonance, much below delta threshold, which is an isoscalar 3+ state. And of course, we would like to know is there more in this situation. And let me first go to the early predictions. To my knowledge, Dyson and Zhang was the first who pointed out the possibility of 6 non-strange states. And it was then Jeffy in 1975 who proposed the H-dibaryon bound lambda-lambda system. And thereafter, there were a multitude of predictions of a vast number of dibaryon states. And we had the so-called dibaryon rush area, many experimental claims of bumps, of hints for dibaryons, but finally nearly nothing survived. Maybe only a single one, firmly established one meanwhile. That's possibly the only survivor, the 1D2 resonance, or say it's a resonance in the proton-proton 1D2 partial wave. And you see it maybe best in the total cross-section of pi d going to proton-proton. And if you look on this reaction, as well on other relative reactions like proton-proton going to proton-neutron pi plus, or proton-proton scattering and pi plus d scattering, and do all a combined phase shift analysis, as has been done, for instance, by a side group, you indeed see in the argon plot very nice circling. That means you see the necessary condition for a resonance. As we know, circling in the argon plot does not mean it's a sufficient condition, but it's a necessary condition. So this would be a state, isovector state 2+, with a mass just something like 20 MeV below the nucleon delta threshold, with a width of the delta. And that's, of course, a complicated situation, that we have again a width like the delta. And the question is it really, or is it maybe a cusp, a vertical state, or just a reflection? All of this has been discussed in literature with many. Let me here just a remark on a very recent, a work from Kukulin at Platonova, who looked on this thing again and found, yes, there is partly a conventional explanation, but you need to have this genuine resonance in order to understand all the data, be it cross sections or polarizations. So let me conclude from the failures in the Dibaryon rush area that one has to do, of course, exclusive and kinematically complete measurements to see some serious structure. Our approach was with a vase detector for pi detector and a windowless target, pellet target on the storage ring Celsius, and later on, fortunately, at COSI with a factor of 100 higher beam. We started first in a 2-pion production, proton-proton induced 2-pion productions, and then we followed a trace, which was a so-called ABC effect, known from the 60s in double pionic fusion. And what we then found is that indeed this effect is correlated with a nervous resonance structure in proton-neutron induced 2-pion production. So what we knew from 2-pion production analysis and reactions, that is the following picture. If we go to proton-neutron going deuteron pi 0, then we expect some cross-section from the conventional T-channel double delta reaction mechanism and from the Roper resonance. And what we got, that was still at Celsius, is this kind of data, which, if you like, look already something like a resonance or maybe something else also. And then we moved to COSI and we got this very nice structure, a Lorentzian shape above very low background. That's what we here already see. Double delta reaction, the conventional one. And if you look on the differential spectra, which is shown in this slide, you see here the Dalitz plot with a very strong enhancement here, which is the so-called ABC effect, which gives a sharp spike at the pion-pion threshold in the pion-pion event mass spectrum. And on the other projection, in the deuteron pi 0 section, we see something like a delta. So the idea was that we understand this data by a model where proton-neutron form a resonance. We call it D star. This decays finding 2 deltas, and 2 deltas decay into nucleon pion-pion or in a deuteron pion-pion. And from the angular distribution, we know that this has to be a 3+ state. Now, it did not only look on the pi 0 channel, but also on the charge channel. That's a deuteron pi plus pi minus channel. Here you have 2 idle spins, idle spin 0 and idle spin 1. We can select them into idle spin 0 and idle spin 1, and you see the resonance is only in the idle spin 0 part. Then, of course, the 2-pion production reaction goes also to the situation where we don't have a deuteron kept in the final state, but it's broken up into proton-proton or proton-neutron or proton-neutron here a partition. And I see in all these states, we do see this enhancement, which is due to this Lorentzian shape due to the D star resonance. Of course, if you see such a structure in 2-pion channels, and if it's a S-channel resonance, a genuine one, then it has all to show up in the proton-neutron channel where it is formed. And this is the result from our measurements in the proton-neutron channel, and indeed we see again this structure as a resonance. This is shown more precisely now in the next slides. Once more, that's an experimental crucis for being a genuine resonance. We have to see the neutron-proton system. We have to sense it in neutron-proton scattering. Sorry, go back once more. And here's already is a first complication. If we estimate how big is the effect of such a resonance in neutron proton scattering, we see it's a 1% effect, roughly. So how to see a 1% effect in neutron proton scattering? You won't see much in it in cross-section, but fortunately we have the analyzing power. And in the analyzing power, the amplitudes go in linearly, or the resonance amplitude, and by interference we can, so to say, enlarge a resonance effect. We know how it looks like, because if it's a 3+ resonance, it has to go in analyzing power like P13. That means the resonance effect has to be maximal at around 90 degrees. That shows the measurement we did at COSY with polarized beam, and you see indeed what was expected before from the best phase shift analysis by a side group was this here, and what is shown here by data is different, and the effect is at maximum at near 90 degrees. We compare this big effect due to this resonance. If we compare it to the measurements we did here of the differential cross-section, which we published later on, and you see it just shows us in the logarithmic plot just at the minimum around 90 degrees as very small effect. So it's largely enhanced in the analyzing power. Now, the data, here's the energy dependence around 90 degrees. We see clearly there is something going on. It's a resonance effect. And in the side analysis, this data enforce that here is a resonance in the 3D3 channel that shows the partial waves. And here we see the Argon diagram, a very nice looping of the 3D3 partial wave. We start here to the pion threshold. That's see here the nice looping. Now let's look on the branching ratio for the decay. So we have here the branching, the measured branching into the diverse 2 pion channels and in the elastic neutron proton system. So the branching into the device 2 pion channels are consistent with ion spin coupling for a delta-delta intermediate system. If we take into account all of the work of Feld and Welkin and Alabaideo and Ozet, that the decay into deuteron and neutron proton channels is of about the same size. Now, what's missing is so far the isoscalar single pion production channel. If the star would decay in such a channel, we should see an effect here at this position. And we see here nothing, and that means a branching ratio which we cannot use as an upper limit on the 90% confidence level is here smaller than 5%. Now let me move now to the possibility that this star resonance is excited also by photons. So gamma D going to neutron pi 0 pi 0. That was the best channel to look at in for this resonance effect in 2 pion production. We see here 3 different measurements. Here the measurement from Forest at ELF, Japan. And we see here they can get only here this upper limit for this star. And the question is this really clean data, or is here background? Because we are just at the edge where pion production can start. So that's a follow-up experiment at Crystal Ball at Mummy, which has somehow better data going more down in the energy. Again, here we see something which could be a signal from this star, but maybe it's also experimental background. And finally, we have new data from ELSA at the BGO ball together with the one dipole in the forward range. They have further reduced the background and see here also possibly the signal. The question is, how big is the sigma we expect? And so far we have only one theoretical prediction, which is the sigma should be in the range between 1 and 2 nanobarns, which is still lower than measure mir. But that's just a prediction. The nice thing here on this new measurement is that it also can, for the first time, provide differential data. Here is an invariant pi-0 neutron mass, and here is the pi-0 spectrum, which actually shows here already possibly some kind of enhancement as we would expect it for the so-called ABC effect. Further hint come from gamma deuteron going to proton neutron, so the breakup reaction. Here is shown again the polarization of the outgoing proton, measured at different labs. In red here JLab data, and that what we see, we have a very strong excursion going to -1, the maximum value of the polarization, right at the position of the star. Now, if you flash this with newer data from MAMI, they have measured the polarization of the outgoing neutron, and we see here both the polarization of the outgoing proton and the polarization of the outgoing neutron. They both give here more or less the same structure. We see here a fall of the polarization down to -1 and then going up. And if we fit it this with a parameter of the D star resonance, it just fits more or less perfect. So the data are still, the error bars are still big, but the structure here is very nice. So let's point out here that both at this position, the proton and the neutron polarization is just -1, around -1. So that means the proton-neutron system must be totally aligned in the S=1 state, as we require, for instance, if the intermediate state would be D star with a 3+ state. So one can also make, or the collaboration with a Legendre decomposition of the outgoing polarization, and as a result, they get that P13 gives the largest contribution. So there's the same situation as we had in proton-neutron scattering. We also see here P13 giving the largest contribution and shaping here, so to say, the experimental result. So let me compare two predictions from quark and hadron models. So experimentally, we know we have the 1+ state of the bound deuteron, the 0+ state of the Werther state, then the 2+ state at the n delta threshold, and now the 3+ state from delta delta. We may compare with the old model from Dibaryons, which more or less by chance or not give the same structure. We also have here newer models from Goldman and Nanjing group, a quark model, and another quark model from the IHAP group of Zhang and all, which work with double delta and hidden color. They also get this structure, and we have the Faraday calculation of Gall and Garcilaso. May I ask how much time I still have?
Sure. You have 6 minutes and 13 seconds.
Ah, thank you. Okay. So let me go to the width. The width may be more interesting than the mass, maybe, or more challenging. In a simple conventional T-channel double delta excitation, we would expect something like 250 MeV, but what we see is 70 MeV. In the quark models, we get around 110 MeV from the Nanjing group. Faraday calculation give also around 100 MeV, and only the calculation from the IHAP group, which works with hidden color as proposed by Stan Brodsky, we get the right number. The question is now, can we say something about the question, is a molecule or is it a compact hexaquark? Now, a very simple estimate may come from uncertainty relation, where the radius is correlated with the binding energy, and our object here is relative to delta threshold is bound by 80 MeV. So we get something like half a femtometer. Similarly, the QCD models from IHAB and Nanjing and LAMP get something like 0.8 femtometer. Now there's also an estimate, a new estimate from lattice QCD from the Hall QCD group, which gets something from 0.8 to 1 femtometer. So this I would like to call a compact object. I think if this would be true, we would have something like a hexaquark. Like in contrast to this, we have the Faddeev calculation with hadronic interaction only. So you get something up to 2 femtometer, which would be something like deuteron-like molecule. Now let me look on the branching. Maybe we learn here something. So if the branching goes like D star decays in double delta, what we propagate, and then the nuclear pion. We have here the relative branching listed in different channels, and compared with if a D star would decay into the 1D2 state, which is at the delta threshold, the dibarium, and a pion. If this decay is correct, then we would not have any branch to nucleon, because we always have a pion here left. So we would have a very strong branch of nucleon pion, but no decay into the nucleon system. That's shown here. So we have a neutron proton system 0 and a very strong branch for nucleon pion system. Now, in the other ansatz, if D star decays on delta, we would have a strong branch into nucleon proton, which we see also experimentally, and nothing, no decay more or less into the nucleon pion system, and that's also what we see. So the experimental obtained branching favor such a situation. Let me assume. So we have a non-strange two-baryon spectrum, probably 3 established states. That's the neutron ground states, the virtual 1s0 state, the 1D2 resonance, and now all this, that's what possibly is exotic, the D star 2380 resonance, which is bound by 80 MeV relative to the delta threshold. So that would be the scenario of Dibaryons in the non-flavored sector. There are also 2 predictions still to discuss. That's either spin 2 state and either spin 3 state. I think I have no time to go into it. We looked on both. We see here evidence for this 1+ state in 2' production as a reaction where we have a so-called associated reaction with a pion. We looked also in 4' production, but so far did not find any evidence for such a state. That would be the situation for associated production in 2' production. I just flashed the slide here for total cross-section. What we would expect from isospin relation and calculation is such a behavior in the 2' production going into proton pi plus pi minus. What we measure is here, so it looks like opening up of a channel, which we can associate with this Dibaryon if you look on the differential spectra, but maybe this will can be discussed in the discussion session. I have no time to go into it. So that's a situation, what I think could be the situation now at the delta n threshold. We have this 2+ state from the 1D2 partial wave. We have possibly in the I2 channel another state here from the 3p1 partial wave initially. And I did not discuss in the delta n threshold the p wave resonances, which have been seen in Cosi-Anki and in site analysis. So that's a further candidates. There are possibly also situations that we have states near the Europa threshold and then star threshold. Again, here the isoscalar single pion production cross-section should open up and go and proceed further on. It does not. It again goes back and can be described by some Lorentzian, whether this is an indication of a state near threshold has to be seen. I go to the outlook. The size of the D star 2380 is, of course, one of the problems which should be solved in future. One possibility would be the electromagnetic excitation of the star in electron scattering and deuteron. And to get here the transition form factor, maybe the transition form factor tells us something about the size of this object. We all look forward to observation and other installations. HARS as at GSI, I think, is still underway. One possibility would be at BAS3 with E plus, E minus collisions, going to something like anti-D and D star in this range, or maybe at KEC, JPark, LHCb, and other installations. I did not discuss anything about astrophysical relevance of such a resonance. And of course, this can be discussed in this discussion session. Mikhail Bashkanov will be there and maybe have some comments on this. The question is, are there more exotic Dibaryons? And of course, one would ask, is there something in the charmed and bottom sector? Let me just point out on the width of a resonance. So if the width of decay products are large, as we have it in the non-flavored sector with large hadronic widths, then of course the resonance will be large in general. But if the width of decay products are small, then also the resonance widths can be small, and that is a charm in the charming and beauty sectors. So here we have a lot of predictions for the diversity of the Dibaryon systems. None has to be seen so far, but maybe there is hope that will be seen in future. And on the last slide, let me just flash here the lattice QSD predictions for such objects. We see here the ratio of the effective range relative to scattering length versus the effective range. And you see here what we know from the unflavored sector. We just have here the deuteron, the only bound state we know so far. We have here the virtual state, NN and proton-proton. And possibly we have something here in the strange sector, or much more charming in the triple charmed sector. So there's hope that if not only bound, but maybe at least as a virtual state, as a resonance, or really as a bound state with Coulomb here, we could possibly see in future something about these objects.
Okay,
thank you very much.
Okay, thank you very much. And so thank you. And now I see already two questions. Christoph, please.
Hello, Heinz, thank you very much for the nice talk. Can you go to page 25, please?
Yes. Yes, here.
You really lost me, because the very first formula you have there, this estimate of the radius, is exactly the size estimate for a molecule, full stop. This is what the Bohr radius is in atoms.
Yeah.
Therefore, if this size is 0.5, the size will not be decisive. And I don't understand the very last line where you get a size up to 2 Fermi if the standard size estimate gives 0.5. How is size defined here? This page doesn't make sense to me. I'm sorry.
I'm afraid I cannot fully answer this question. That's the results given in this paper from Gal and Garcilaso. And of course, what they do is essentially, in this calculation, they say that this star is a construct of the 1D2 resonance at the delta threshold plus a surrounding pion. And in this model, they get this estimate of 1.5 to 2 femtometers.
Okay, then it's just a matter of how, with respect to what threshold you look. But
yes,
but
sure.
You should be very careful with the statement, because if you really want to assign for that thing a delta-delta molecule, the size estimate is really given by the formula, this R being 1 over square root 2 mu b, and then you have 0.5.
Yes, exactly.
Right? But this is not hexaquarks, this is molecule. If you want to talk about molecules, and if the molecular size is of the order of the hexaquark size, there will be no model independent way to disentangle the molecule from the hexaquark. No way.
Well, but if we have a size which as small as a proton of 2 baryons, how can you speak in sense of molecules? They overlaps. These 2 objects must strongly overlap, right?
Maybe this is for the discussion session then.
Yeah. Would be great.
Okay, then we move on. Eulogio, please.
Yes, I have a few comments to make, obviously. Heinz, if you are so kind of to go to page 5, I'll make my first comment.
Page 5.
Page 5, you are cautious to say that possibly that would be a Dibaryon. But this reaction is the one that, we have a paper published, well, that very well. Raquel Molina and myself. And we describe that by means of a triangle singularity.
Yes.
The triangle singularity is also, this has been shown by Compass. The triangle singularities have also, Argand plots. So then, according, to the basic rule in physics, which is if you can explain something based on conventional physics, one has no right to claim something more exotic, then you should remove the claim for that, right? So now let's go to page 19.
Wait. What you calculate is so far only the total cross section.
We calculate angular distributions and we.
I would see the full story of polarization measurements.
Okay. I will go. Wait.
Side analysis.
There will be next
all
question.
The measurements.
It will be next question. Yes. Okay, so go down to page 19. Page 19, which is the beautiful picture that we all like so much. Page 19. Sorry. Page 9. 19 will go later. Page 9, sorry. I'm sorry. Page 9, okay, that thing, yeah. Okay, then as you also know, it is not me, it was Barnier in 1973 who said, this was reproduced, by a sequential, by one pion production. A neutron proton going to pi minus proton proton, followed by proton proton going to pi plus neutron. It was not me, it was Barnier. And we simply follow, the idea of Barnier, and we have to acknowledge that he was right. And that's why we wrote, this little paper that we will polish. We are doing more work on it. Yeah? So you see, there is an alternative explanation again for that without the need to invoke, the Dibaryon. Okay. Now, if you go to page 11, if you go now to page 11, I have told you that very many times, but I want to repeat it because there are new people in the audience. They are in the pictures below. You say that this extra contribution is due to the Dibaryon, and you see there, some bending there. That looks like. Okay, well, the thing is that, there are 2 independent papers, one by Colin Wilking, the other one is by Miguel Albadalejo and myself, in which we show that this is true, that this contribution exists, as far as, you have, the peak that you have in the fusion reaction. But it doesn't mean that that comes from a Dibaryon. You get that whatever the origin of the peak that you have for the double pion production, whatever reason is for the double production. As soon as you have the double production, the peak, this is a necessary consequence, and that is what we prove. But independently of which is the reason of the peak for the double pion production, it doesn't matter. Whatever is the reason, this is unavoidable, and that's what Colin Wilkin and Miguel Albadalejo and I did independently, showed independently. So now, if you
let me just respond. Okay, you talked about these 2 spectra, pi 0,
Yes.
pi 0, and pi plus, pi minus.
Yes, and the other one.
What
the
about
first-
pi minus,
the
pi
first
0?
one, same one. I mean, well, that one, yeah, okay, that one we didn't do. But anyway, I mean, we could, I mean, equally do. But anyway, I mean, the first one we didn't do, so I don't want to talk about that. But the other two, I mean, we proved. We proved that whatever the origin for the double pion production, I mean, this is unavoidable. You will have this as a consequence.
Yes.
So, okay. Now, can you go to page 11? I mean, little by little, I mean, page 11.
I'm at 11.
Page 11, yeah. Okay, I mean, 11, great. Yeah, you are in 11, yeah. So fine, because I mean, you have the, I mean, also the asymmetry and the analyzing power, and you are right. I mean, that is true. I mean, and I don't dispute that there are signals there, but these signals are also necessary, you know, they are necessary, they are a necessary consequence of the peak that you have in double pion production. Why that? Because you see, you can have Pn go into d pi pi, followed by d pi pi go into Pn. So, you know, and this goes into the inelasticity, you know, this goes into the elasticity of the phase shifts or the amplitudes that you have, I mean, for Pn going to Pn. So if you have a peak there, I mean, you are going to see that in the inelasticities, you know, and then it will have this repercussion. But again, this you will have as a necessity independent of what is the reason for the double production peak, whether it's Dibaryon or what Barnier said. It doesn't matter. Whatever is the origin of this double peak of the peak of the double pion production, you will have that in the analyzing power. Okay. Now I mean,
Eulogio, I would like to give the opportunities also to other people to ask questions.
I finish. I
Okay.
finish with one more thing, and I have finished. Okay.
Okay.
Go to page 18, and I have finished. I promise. Yeah.
No, maybe,
18.
maybe
18.
discuss these things in the discussion.
We will discuss
session.
more. Yeah, sure. We will discuss more. But I mean, I want to see page 18 because this is very instructive. You know. Page 18, and I will finish with that. I promise.
18.
See 18. 18. Okay. Okay, that was, I mean, lots of hopes, you know, that you would see there, I mean, the Dibaryon peak, and you don't see anything, you know, I mean, that the fact is that you don't see anything there. And since we will discuss more later, I mean, I want to call the attention to the audience, I mean, to the last figure, the one of Jude, very recently in the PDG. I find that a little bit exaggerated. I don't know how you see that. But I will show you later in the discussion session my own fit into this data with a straight line that doesn't require 3 Dibaryons, not 1, 3 Dibaryons.
Okay, but then you show that in the discussion.
Yes, I finished.
Okay, thank you. Thank you very much. So I have now on the list, Michael, please. And then Søren.
Heinz, could you go to page 5? I just want, so for people who are not familiar with Eulogio, so you should take his words with a lot of caution. So for example, he just stated that they explained this 1D2 resonance perfectly nice with triangular singularity. In reality, they used mass of delta, which is 10 MeV smaller than the real delta. And that's usually exactly what you expect for molecular state. And only that way they explained data, and they only explained cross sections, even not well enough in a very limited range. So then he said they explained it. It's not really true.
This is well, that's your
okay. I think that's a very good starting point for an extremely interesting discussion just after the break. So if you all agree, I would move that to later and move now to Søren, unless also Søren has the same point on this slide. Søren.
No, different slide and different point, maybe.
Okay, so please go ahead.
Yeah, page 11 also. I would like to.
Okay, 11, yes. People like it.
I noticed that the black points in the plot top right. Yeah.
Yes.
Which is D pi plus pi 0. And I was wondering, is it clear that there's really no charged partner of that state? So because that D pi plus pi 0 would.
Yeah, no. What is missing here is measurements from at higher energies. And what you see here is nothing else than the double delta excitation in the idle spin 1 channel. So you see my pointer? No.
Yes,
Yes,
yes.
I can see the pointer.
So, so the experimental data go like this. And it's a broad state which can be explained by the conventional T-channel double delta. Is that an explanation?
Yeah, I was just wondering if there's, I mean, if it's really a hexaquark, you can exchange the U and the D quarks. You can have, I don't know, UU bar, and then you get charged partners, basically.
No, but it's isoscalar 0. You can't have any partner.
Yeah, okay, that goes in as a, yeah, that's the reason. Yeah, thanks.
Okay, with that, I would just close the discussion for this talk, and thank you very much for the nice talk, since it triggered a very active discussion. Now, I would like to know from the organizer if it is okay, because the coffee break should have been 2:25, what's already done. If you want to reconvene at 2:40 or, for example, 2:45, so we give 5 minutes more.
Okay, let's say 15 minutes break as from plan. We are very happy that we have a so active and reactive audience to this workshop. So Heinz gave us a lot of hint for the discussion in the afternoon, and let's reconvene in 15 minutes. Thank you very much, Titi, to chair this.
How much? 15 minutes?
Shall we try?
At what time?